Hey guys, in this video we're going to talk about 5.2 in the textbook, the definite integral, and 6.2, constructing antiderivatives analytically. Alright, so the first thing we need to do is talk about what an integral is. Alright, so this whole semester we've been talking about derivatives, and we're now at the point in the semester where we're going to start talking about integral calculus, okay? So when we integrate a function, all we're doing is we're looking for the area under the curve, the curve and the x-axis typically. So for example, I have this function y equals negative 5 over 2x plus 5, and suppose that I'm interested in the area under the curve that is bounded with the x-axis, so that's where we stop. All right, so we want to figure out what that area is. And some functions are easy to find the area of, like this one. So the way that we set this up in integral notation, and I'm gonna go more in depth what these parts mean later, but what this means, when I say find the area under that curve, what I'm really saying is find the area starting at when x is equal to 0, which is this point, all the way up until x is equal to 2, and that's this point. So I want to, use those x values as my starting and ending points. So that's what these numbers at top tell us. These are the starting and ending values. And then what comes here is the actual function. What are we trying to find the area? What curve are we looking at, right? This dx, I'm gonna get into this in a minute, but for now, just ignore that. And so, yeah, I have this in the box. This means find the area starting at x equals 0 and ending at x equals 2, okay? So what is that area? Well, if we look at this is a right triangle, right? I know how to find the area of a right triangle. The area of a triangle is just base times height over 2. And the base of this thing, what's the length of the base? Well, that's 2, all right? And what's the height of this triangle? Well, this triangle is going to have a height of 5. All right, so the area of this triangle is just 2 times 5 over 2, which is just 5 units squared. Okay, so in integral notation, and we're gonna get a little bit more rigorous with this, but I'm just introducing this, so I want to make sure that I don't overload you here. So in integral notation, what is this saying? This is saying we'll find the area between 0 and 2 of the function, and that is going to equal 5 units squared. All right, so here again, we're going to evaluate this definite integral. Later on, I'm going to talk about, definite versus indefinite, but for now, just know that definite has these starting x and ending x values. So here's a picture of the curve that we're integrating, and we start at x equals 2, which is right here, and so we want to know what this area is right here, and then we're going all the way up to x equals 7, which is this area. Now, if I just talk about area, I don't care about negatives. However, there's a little bit of a distinction with integrals, okay? If I'm asking for the total area of this, I would just take the area of this and add it to the area of this, right? But I'm not asking that. I'm asking to, I'm asking you to give area a sort of direction here with this integral business. And so what I'm trying to say is the area that's below the x-axis is going to be negative area, technically, when we're evaluating the integral. And above the x-axis is going to be positive. All right. So to take into account the negative area, I'm just going to give it a negative sign, basically. All right. So let's go ahead and do this. All right. So the first thing we want to do is figure out what that quote-unquote negative area is. I really shouldn't be saying that, but we want to find out what that, what sign to give the area, or what number to give the negative value of this integral. So let's go ahead and just compute this like we normally would. Base times height over 2. It's a triangle, right? And so the base here is 2, and the height is 4. And so for my first piece, so for this piece, let's draw it the other way. So for this piece right here, I just have negative base times height over 2. And so I'm just getting negative 4. All right, so negative 4 units squared. All right, so then I have to take the area of this guy, this triangle that's above the x-axis. So here, the base of my triangle is going from 4 to 7. So it's going to have a base of 3, and it looks like it has a height of 6. And so computing the area here, giving it a positive sign, we have base times height over 2, and that's going to give me 9 units squared. All right. So combining these together to find, the value of this integral, we're just going to do negative 4 plus 9 to give us a net value of 5 units squared. So that is our answer here. Now, the answer would be different if the directions were this. If the directions said, find the exact area without any kind of integral symbol like we have here. And by the way, that symbol, it looks like an S, doesn't it? And the reason that it looks like an S is because it stands for sum. And we're going to see why in just a few slides. But if it said find the exact area, we're not treating, we're not giving the area a sign here. We're just trying to see how much ground is covered. And so our answer here would just be 4 plus 9 is 13 units squared. So there's a distinction. If we have an integral, we are accounting for the negative area. If we don't, if it just says find the area, then, we don't account for the negative area there. All right, so let's go ahead and do this one. Okay, so we're trying to find the definite integral, and so we have, we have our starting value is x equals 5 to x equals 12. So let's go ahead and shade what we're trying to find in orange. So x equals 5 starts here all the way to x equals 12 is right there. And this guy, we're going to give him a negative sign, and it's a triangle. So the area of this little triangle under here, it's going to be, well, let's give it a negative sign. So base is going to be, let's see, 1, 2, 3. So that's going to have a base of 3 times a height. That height is going to be 3 units long as well, divided by 2. And so the area of that portion is negative 9 over 2. All right. Now, what about this circle right here, or this semicircle? How do I find the area of that? Well, if you recall, the area of a whole circle is pi r squared. Therefore, the area of a semicircle, half of a circle, is just going to be half of pi r squared. So pi r squared divided by 2. Okay? Now, what is r here? Well, r is the radius, so the distance from the center to the edge is going to be 2, all right? And so the area of the semicircle is going to be pi times 2 squared over 2, which is going to simplify to 2 pi. And did I do this right? Let's see. Okay, yeah, I think so. So this is going to be, right, 2 pi, okay. So base times height over 2, base times height over 2, okay. All right, so all together, what is our answer going to be? Well, all together we have, why is this gray? We have negative 9 over 2 plus 2 pi. That's our answer here for that, that integral. All right. Now let's look at the second one. It asks us to find the area from 0 to 12. All right, so let's just go ahead and get rid of some of this. Okay, so this time we're starting at x equals 0, and we're going all the way to x equals 12. Well, I'm going to just, we already found the area of this piece. The area of this piece, we said, was 2 pi. All right, so now all that's left is this guy and this guy. All right. Now I could, I could use the fact that we found the area of the triangle, but what I'm going to do is I'm going to look at this bottom part as a trapezoid to find the area of this. So the area of a trapezoid is just equal to a plus b over 2 times h, where a and b, so a and b are the bases, the top and the bottom, and h is the height of the trapezoid. All right. So the area of this trapezoid, again, we're going to give it a negative sign because it's below the x-axis. So we have the following. We have, well, the first base, this one from here to here, let's see, we're going from 2 to 8. So I believe that is going to be 1, 2, 3, 4, 6. So we got 6 is one of our bases. Then the other one is 2, if we count. All right, so we have 6 plus 2 over 2 times the height of this trapezoid. Well, what's the height? The height is just going to be, I'll do this in purple, 1, 2, 3. The height is going to be 3. So the area of this trapezoid, and I'm going to put a negative on it. So this is going to be negative 12. All right, so let's mark that up here. Okay, so this is the area of this trapezoid is equal to negative 12. All right, now the last thing we need to do is find the area of that little orange trapezoid all the way to the left. So again, we're using our trapezoid formula. Base plus base over 2 times height. Well, my top base is 1 unit long on this orange trapezoid, and my bottom base is 2 units long. All right, so the area of that top trapezoid, so we got base plus base over 2 times the height. The height is 1, 2, 3. So the height is 3. So this is going to give me 9 over 2. And it's positive because it's above the x-axis. So the area of this guy is 9 over 2. All right, and so we just add them all up to get our final area from x equals 0 to x equals 12. And so my final answer here, well, I have 9 over 2 minus 12 plus 2 pi And simplified, I mean, this is, 2 pi minus 7.5 basically. So that is going to be our area from x equals 0 to x equals 12. All right. So that's all fine and good, but what is the difference between this curve that we have, f of x equals x squared, and the other ones that we just dealt with? Well, the other ones we were able to kind of like parse into geometric shapes that we know the area formulas for, right? Like here we change this into triangles to compute the area. Here we have trapezoids and a semicircle. But what if we have something like just, something weird like this, right? It's not a straight line, so we can't, use the area of the triangles. So what do we do in this case? If we're trying to integrate from 0 to 1 under the curve x squared, what we can do is we can approximate. We can't get an exact answer quite yet. We will by the end of this lecture, but we can approximate. Here we got exact answers because of those geometric formulas. These were perfect geometric shapes, so we were able to find the area under those curves, but here it's weird, right? Things are, stuff's getting weird. So what we're going to do is we're going to use the idea of approximating the area by using rectangles, okay? So here's how we're going to do it. Let's start with 3 rectangles. Well, I'm integrating from x equals 0 to x equals 1. So I basically, if I'm using 3 rectangles, I basically want to split that interval into threes, right? Into thirds. And so, the first thing I need to do is find out the width of my rectangles. They're all going to be the same width to, keep things easy. If you carry on with math and take some math classes in grad school, you're going to start integrating with you're going to use rectangles that have different widths. But here, let's just keep it simple. All right, so find out the width of each rectangle. How do we do it? So we take the interval a plus b and divide it by 2. Now here our starting point is 0, x equals 0, plus x equals 1. Actually, I'm sorry, we're dividing by 3 because we want 3 rectangles. So take the interval, divide it by 3, and so the width of each rectangle is going to be a third. All right, so let's go ahead and just kind of draw that in our picture. We have this rectangle from 0 to 1 over 3. So this is my first width of the rectangle right here. And then I have 1/3 to, well, what comes next? If I add a third to 1/3, 2/3. So that width is also a third. And then from 2/3 to 1, well, 1 is the same thing as 3/3. So again, this is going to be a third. This is another third right here. All right, so we have our 3 rectangles. Let's go ahead and just kind of, draw them in a little bit. So I'm going to say, well, on the curve, the height here is right there. And then I'm just going to draw in a rectangle like that. So here's my first rectangle, this red guy. Can you see that? The length and the height right there. Okay. And then my other rectangle has a height. So when x is 2 over 3, the height is right here. And then I just kind of carry that height over to make it touch that one. All right, so there's my other rectangle. And then my third rectangle, well, my height at 1 is right here. And then I just carry that over and drop down to make that third rectangle. All right. So what I'm going to do is I'm going to take the area of these rectangles and add them up to give me an approximation of the area under the curve. Now this isn't going to be a great approximation because, well, look at what's happening. Like if I take the area of the blue rectangle, I'm getting all of this, right? But I don't want to count this part, you know? So I'm kind of overestimating my area here. But that's okay. So, you know, I'm just trying to figure out, again, you know, I can't stress this enough. My main mission is to find the area under this curve that I highlighted in orange, okay? So let's go ahead and approximate that by taking the areas of the rectangles. So how do I find the area of the first rectangle? That red guy. Well, the area of that red guy, remember the area of a rectangle is base times height, right? So the base, each of these rectangles we found to be, you know, like they have a width of a third, right? So we have width times the height. Well, what's the height going to be? Since this is a function, the height, okay, and this is important, this is very important. So the height is going to be f of, you know, whatever your right endpoint is in this case. So like we're basically plugging in, you know, our x value into the function that we're trying to find the area under. So this is going to be f of a third. Maybe I'll keep this in red. So that, you know, that's going to give us the height. Plus, now we need the area of the yellow rectangle. Oops. Shoot. Let's do the area of the yellow rectangle. So again, the base of this yellow rectangle is still a third, right? But this time the height is going to be f of, well, the height is f of 2 over 3 because it's asking, you know, what's the y value when x is 2 over 3? That's our height. So this is going to be f of 2 over 3. All right. And finally, the area of the blue rectangle, again, it's going to have the same width of a third. That's how far 2/3 is from 1. So we got a third. We got a third times f of, well, what's the height here? We're looking at the height when x is 1, right? So the height is going to be f of 1. And really think about that. Wrap your head around that. Why is that the case? Okay. All right, so let's go ahead and do this computation. Now, f of x we were given as x squared. So that means that f of a third for that red piece is going to be 1 over 3 squared, which is 1 over 9. So that's 1 over 9. And we do the same thing for the others. So f of 2/3 is simply 2/3 squared. That's the height. That's 4 over 9. So this is 4 over 9. And finally, f of 1 is going to be 1 squared, which is, of course, 1. So this right here is 1. All right, so let's write this again. Let's do some cleanup here. Write this again. Where are we at in time? Okay, good. All right, so the area of the red, we have a third times a ninth. Total area, a third times a ninth, plus the area of the yellow, which is a third times 4/9, plus the area of the blue, a third times 1. Now, if you put this in the calculator, you add it all up. Let's see. I did this beforehand, thank God. We get 14 over 27. And we expect this, again, when we found the area, we found all of this, right? We found all of this. This whole thing is 14 over 27 when you add those areas up. However, we're only looking for this part, this purple part. So we have an overestimate of area. Okay, so let's write that. So this is an overestimate. All right. But we can do better than that. And how do you think we can do better? So let's see. Let's look at the next slide. Well, the more rectangles we have, since we're making the rectangles so that they have the same width, the more rectangles we have, the skinnier they'll be, and the better the approximation will be. All right, so let's just do this with 5 rectangles now. All right, so what are we going to do first? Well, we'll go ahead and get our points on here. So if I divide 1, 0 plus 1 divided by 5, that means that each of these pieces should be a fifth. All right, so we got 1/5. Let's do it in rainbow. That'll be fun. 2/5, 3/5, 4/5, and 1 is 5/5. All right, so let's go ahead and just sketch our rectangles. So here's our first one. My second one. My third one. And my fourth one. Well, I need a fifth one too. Forgot about that. Okay, so there we go. There's my fourth one and then my fifth one. So 5 rectangles. Where's the blue? There we go. Okay. All right, so there's my 5 rectangles. So this should give us a better approximation, right? Because, the width is skinnier and we have less area on the outside than we did here, So let's go ahead and and do this. All right, so let's see. For our red, well, we have a fifth, that's the width, times the height of this thing is f of a fifth. And we just do the same thing that we did before. Again, for orange, it's same width, but this time our height is f of 2/5. Blah, 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 blah. Okay. So these are all the areas. Okay. All right, so let's go ahead and do this. Okay, so f of 1/5. Again, our function that we're concerned with is x squared. So the height at x equals 1/5 is going to be 1/5 squared, which is just 1/25. And just do the same thing for all of these. I'm just squaring each of these inputs. All right. So let's go ahead and add all the areas up. I have a fifth. And by the way, I can factor out a fifth, right? Because if I'm adding all of these areas, each of these has a fifth in common. So I have a fifth times 1/25 plus 4/25 plus, that's, orange, red, orange, yellow is 9/25, 16/25, and blue is 1. So this is the total area of the rectangles. All right, so let's go ahead and count these up. All right, so I'm getting, all right. So the big point here is that this is a better approximation than, this was a better approximation than this. And why? It's because we use more rectangles. We're getting closer to the actual real area under the curve there. Now, where do you think we're going with this? I'm going to show you where we're going with this. All right, so here is x squared, and it's going from 0 to 2 instead of 0 to 1, but the point is the same. As the rectangles get skinnier and skinnier, the area under the curve, the area that we're getting for that sum of the rectangles is getting closer and closer to the actual area under the curve. All right, so let's go back to this. All right, and so I just said that the more rectangles we use, the better the approximation of the area under the curve. So let's say that we were approximating the area using n rectangles instead of 3 or 5. Let's just say we have an arbitrary n. And let's say that n is going to infinity, right? Because that's kind of what we want. We want this thing to, we want, infinitely many skinny rectangles. That would be ideal, right? So if we took our interval and divided by n, well, each rectangle's width would be 1 over n instead of 1 over 3, 1 over 5, whatever. So we have 1 over n, 2 over n, infinitely many other ones until we get to n over n, which is 1. So you can imagine, I obviously can't draw infinitely many rectangles here, but you can imagine, and I didn't even draw these intervals great, but you can imagine just how if they were super, super close together, 1 over n and 2 over n, we had infinitely many of these rectangles, eventually we're going to get very, very close to the actual area under the curve, which, again, is this weird shape. It's not a triangle. It's not any kind of geometric shape that we have a formula for because of this curvature right here, So the area using n rectangles, again, we can just say, let's just keep doing what we've been doing. We took the area of the first rectangle, which was width times, this is just going to be f of 1 over n, plus the second area, which is also going to have a width of 1 over n, times f of 2 over n, etc., all the way up until 1 over n times f of n over n, which is just f of 1. Maybe I'll write that here, actually. F of 1. Okay, so this is our area, and again, we don't know exactly what n is, but this is just something to think about. All right, so the examples that I did, we used right-hand sums, and all that means is that I'm taking the height to be the right point on the rectangle. So for this one, I took the height to be f of 1/3, and then I took the height to be f of 2/3 for the second rectangle, f of 3/3 for the third rectangle. But we can also approximate the area under the curve using the left endpoints, right? So, all we're doing is we're taking the left endpoints instead of the right endpoints and saying that's the height. So here the height is just 0, right? From 0 to 1 over 3. So that rectangle technically doesn't have any height. And then over here, the height of the second rectangle is at f of 1 over 3. And then the third rectangle has a height of f of 2 over 3 instead of f of 1. All right. So, and here's the areas. This is the way that we wrote the right-hand sum before. And the left-hand sum we can write in a similar way. Right? We still have the same width, but the height is changing based on the left endpoint's height. So like 0, f of 0 is 0. And actually, let's go ahead and just compute this stuff. So this is the notation, by the way. I'm sure you guys have seen this in a previous class, but this is called summation notation. And basically, we start at I equals 1, plug in 1, and just keep going from there until we get to n. So like let's write this out. Let's write this out in our example. So we're going from I equals 1 to n, which is how many rectangles we are partitioning, or like how many rectangles we have. So we're going from I equals 1 to n equals 3. Delta x is the width of the rectangle, all right? So delta x is the width of the rectangle. So we have a third, in this case, times f of xi, all right? So what does this look like expanded out? Well, we start at I equals 1, so we have a third times f of x1, right? We're replacing I with 1, plus, then do it again, but now this time I is 2, so we have a third f of x2, and finally, we have a third times f of x3. So that's what this summation notation looks like, all right? Now, x1 is going to be, so x0 is the very first point, x1 is the second one, and so forth. And so, And so what we have here is so x1 is 1 over 3, x2 is 2 over 3, and x3 is 3 over 3, which is 1. x0 is just 0, all right? But for the right-hand sum, we don't need x0. All right, so let's go ahead and compute this. So this is equal to a third times f of a third plus a third times f of 2/3 plus a third times f of 1. All right, and again, this is just coming from our x squared, right? That's our function. So if I take this and square it, if I take this and square it, if I take this and square it, what I end up getting from my right-hand sum is 14 over 27, which we saw was an overestimate. So we already did this one. Now let's do the same thing using the left-hand sum. So this time the left-hand sum, it's the same idea with the summation notation, but instead of going to n equals 3, we're going up to 2, right? We're going up because, again, this is, let me write this here. This is x0, x1, x2, x3. All right, so expand, and again, delta x in this case is a third. That's the length of our rectangles. So we have a third times f of 0. Well, I wrote it up here, actually. So that is what the summation notation is written out. And we can compute this. So let's go ahead and do it. We have a third times 0 squared plus a third times a third squared plus a third times 2/3 squared. And let's see what that gives us. So this is going to be 5 over 27. And just looking at this picture, do you think that's going to be an overestimate or an underestimate? Well, it's going to be an underestimate because I don't have this area which I need, and I don't have this area which I need. So that guy is going to be an underestimate. So this is an underestimate. All right, let's see. Okay, I'm going to go ahead and stop this video and we'll pick back up on the next one. Thanks for watching. I'll see you guys next time. Okay, so we want to use the table to estimate the area under a curve f of t from x equals 0 to x equals 20. Okay, so when we want to use the average of the left and the right hand sums. So let's go ahead and just kind of like sketch out what we have here. So we have our t values starting at 0, then we have 4, 8, 12, 16, and 20. So it looks like our rectangle is going to have a width of 4 for each of these. Okay, so let's go ahead and list our points. So it says when t equals 0, f of t is 1.8, so that's our height. When t is 4, we have a height of 2.3. I'm just being kind of sloppy here. At 8, we have our height is 5. At 12, it's 6.9. At 16, it's 8.4. And at 20, it's 11. All right. So let's go ahead and just sketch our rectangles here. So we have this guy. So I'm going to do the right endpoint first. So I'm taking the right endpoints and I'm just connecting to make a rectangle. So I'm going up, over, and connecting, up, over, connecting. Okay. So I'm trying to find the area of these 5 rectangles. So for my right endpoints, so let's do this in purple actually. So my first one, well, we're all going to have a width of 4, so I'll factor that out. So my first one, we have a height of 2.3. All right, that's my first one. My second one, I have a height of 5. Then 6.9. Then 8.4. I should have extended this a little bit. Let's see. Plus 11. All right, so I have 4 is my width for all of these, so that's on the outside. And if I do this in the calculator, let's see. I got 134.4. All right. Now let's do the left endpoints. So this time I'm taking my height to be the left endpoint. So like this is my first rectangle. I'm going to do it in orange. My second rectangle. My third rectangle. And so forth. This is my left endpoint. So I'm not using that far right one. All right, so again, the width of all 5 of these rectangles is still 4. So I'm going to go ahead and factor it out. And this time the height is coming from the left endpoint. So this first height that we have here is at 1.8. My first rectangle. Then 2.3. Then 5. Then 6.9. And finally 8.4. And let's see what we get when we do that. All right, so we get 97.6 is my left endpoint. And so the average between the two, so we take our right plus our left, and we divide it by 2. And our final answer here is 116. So that's the approximate area. All right, so suppose the following measurements were made for a function f of t at various times seen in the table. construct and evaluate a Riemann sum using the left endpoints for each of the t-axis intervals. So what we've been doing, these sums, these are called Riemann sums. And the integral that we've been looking at is called the Riemann integral. All right, so let's go ahead and do this. Now it's just asking us to use the left hand. So, I mean, I guess we can draw a picture. It doesn't matter. So, our first, it's saying that our first time or whatever, that's our independent variable, is 0. So this is 0. Then our second one is at 0.5. So this is 0.5. And notice that it looks like our widths are different here. So let's just, keep that in mind and be kind of careful. The third point is at x equals 0.75, or t rather. And then finally, we have our last point is at 1.5. All right, and the y values are all in this column. So at 0, we have 3. At 0.5, we have 1. At 0.75, we have 2. And at 1.5, we have 0.5. All right, so looks something like this. All right, so let's go ahead and use the left endpoints here. So this is my first left endpoint, so I'm going to take the height of this. I'm going to find the area of that rectangle. And the second one, this is my width, this is my height, this is my leftmost endpoint for this interval. And that's that. And then here's my third left interval. So I want to take this guy. And that's it. So let's go ahead and do this. So remember the area of these rectangles, we have length times width. So the first one, the purple one, has, a width of 0.5 and a height of 3. Then the second one, we have a width of 0.25 times, well, this height is 1. Yeah, so we have a height of 1. Plus, this width between 0.75 and 1.5 is 0.75. So this is 0.75. So that width is 0.75 times the height, which is 2. And altogether, if we sum this up, we get our answer to be 3.25. And this question is just asking for the left-hand sum. So that's all we have to do there. All right, suppose g of x equals a fourth x. Compute the Riemann sum on 0, 4 using 2 equal intervals and the right-hand endpoints. All right, so that's what we're doing here, right hand. And then do the same thing using 4 equal. So let's do our 2 equal intervals first. We need to partition 0, 4 into 2 pieces. So basically we're just doing 0 plus 4 divided by 2. And that means that each piece is going to have a width of 2, basically. So here is 4, and then from 0 to 2 is right there. Maybe I should have made this a little bit. So 0 to 2, 2 to 4. All right. Here's 0, 2, and 4. So there's our interval from 0 to 4. And we partitioned it into 2 equal widths from 0 to 2 and from 2 to 4. And so let's look at the corresponding heights. Well, when x is equal to 0, if we plug it into our function here, 1/4 times 0 is just 0. So that's our first point. Then when x is equal to 2, if we plug it in here, 1/4 times 2 is 1/2. So this height is going to be 1/2. And then finally, if we plug in 4 in for x, a fourth times 4 is 1. So that's going to be like this. It's going to be linear. And there is our nice little function. So let's go ahead and use our rectangles at this point using the right-hand endpoints. So from this first interval, 0 to 2, my right-hand endpoint is here. So that's the height I'm using. And then on the other one, my right-hand endpoint is there, so that's the height that I'm using. And let's take the areas. So for 2 equal intervals, I have, well, my width for the first one is 2. My height is a half. Plus, again, the width is 2. And now the height this time is 1. So this is going to give me an area of 3 using the right endpoints. All right, now let's look what happens when we have 4 equal intervals. So 4 equal intervals. Well, again, we're just doing 0 plus 4, but this time we're dividing by 4. And so that's going to tell me these rectangles are going to have a width of 1. So this is 1, 2, 3, 4. So again, my first, when I plug in 0 into 1/4, so 1/4 times x. When I plug 0 in, I get 0. When I plug in 1, I get a fourth. When I plug in 2, I get a half. Let's do this again. Let's do it like this. When I plug in 3, I get 3/4. And 4, I get 1. So I know it doesn't look great. It's supposed to be a straight line. All right, let's do our intervals. So again, we're using the right-hand endpoint. So that's that here. Here's my right here. So that's my height. Right. Drop it down. Right. Drop it down. Okay, so let's find the area of those rectangles. Okay, so the width of each of these is going to be 1. So for the first rectangle, width of 1, the height is a fourth, plus, again, 1 times a half, plus 1 times 3/4, plus 1 times 1. And that's my area there. And this is going to give me an area of 2.5. And we should expect that this one is more accurate because we used more rectangles with a skinnier width than we did with the 2 rectangles. So how do we prove that this one is more accurate? Well, since this is a line, we can actually find the area, the exact area, using the triangle formula from geometry. So let's do that. So, all right. Actual area. So we know that the width is going to be 4 of the triangle, right? Because we're going from x equals 0 to x equals 4. And this height right here is f of 4, which is just 1/4 times 4, which is 1. All right. So this is a height of 1, base of 4. So area is base times height over 2. So our area is actually 2. This is the actual area. And we can see that the second estimate was better. 2.5 is closer to 2 than 3. All right, let's look at this example. So let's see where we're at in time. Okay, we're good. Okay, so we want to consider, again, we have a linear function, negative x plus 8. So yes, we could find the exact area because it's linear and we could just break it into a triangle. But let's go ahead and estimate using 4 equal size intervals, meaning 4 rectangles, on the interval x equals 0 to x equals 8. And now they say, here we're using let me do this in a different color. They tell us that xi is the left-hand endpoint, so we're using a left-hand sum here of the ith interval. And, do we expect it to be an overestimate or an underestimate? All right, well, let's go ahead and just kind of sketch out a picture. We want 4 rectangles, starting at 0, ending at 8. So 0 plus 8 divided by 4 equal pieces is going to give me a length, or a width of 2. So our rectangles are going to be 2 units long in this case. All right, so we have 2, 4, 6, and 8. Okay, so what was our function? What was it? It was negative x plus 8. So we have f of x equals negative x plus 8. So if I plug in my first endpoint, 0, and we're using left-hand endpoints for the ith interval, okay? So what does that mean? x0, so that's the 0th interval, right? it's the first interval, but we're calling it the 0 interval, and we're calling it, so this is the 0, x0, x1, x2, x3, and x4. All right, so if we plug in 0 in here, we're gonna get a y value of 8. If we plug in 2, x equals 2, we get a y value of 6. When x equals 4, we get 4, and we can see where this is going. We get 2. I can't draw lines for some reason. And finally, we get 0. All right, so, this is supposed to be a straight line. So we're concerned with the area under this curve. That's what we want to answer. And we're using 4 rectangles to do this. Now they're telling us to use the left-hand endpoint, so the only endpoint that I'm not using technically is that one. All right, so for the first rectangle, here's our height using the left-hand endpoint. Our second rectangle, here's the height using the left-hand endpoint. Third rectangle, here's the height. And fourth rectangle, here's the height. Sorry. Okay, so there's our 4 rectangles. Let's go ahead and find the area. So the width for all of these is going to be 2. So let's factor that out. And then the height is going to be, the y value of the left-hand endpoint. So the first rectangle has a height of 8. The second rectangle has a height of 6. The third one has a height of 4. And the fourth one has a height of 2. So that's that. The area is equal to 40. So this is an estimation. This is an overestimate in particular, because we can see that, these pieces above the curve should not count in our actual area, right? But there's more area there than we actually have, so this is an overestimate. And if we were to compute this using the triangle formula, we would see that the area, base times height, so we have our base is 8, our height is also 8, right? So base times height over 2 is 32. So this is the actual area. And 40 is an overestimate. All right. Okay, evaluate the definite integral from -1 to 1, the square root of 1 minus x squared dx. Okay. So how do we do this? Well, the first thing to recognize is that this is our function. So our output, our y value is 1 minus x squared. And so what we can do is do some manipulation here. If we square both sides, we get y squared equals 1 minus x squared, and finally add x squared to both sides to get y squared plus x squared equals 1. Now, because we're only given a positive version, this is a, this is a circle centered at the origin, right? This is a circle with radius 1 centered at the origin. But since we're only given the positive value of this, it's going to be a semicircle that has radius 1 centered at the origin. So this picture, and you could use Desmos to look at this if you wanted to, but this picture looks like this. So here is, that's a terrible semicircle, but that's what it is, all right? It's centered at the origin, and here's -1, and here's 1. My radius is 1. So we're trying to figure out what the area of this is. And what we can do is we can just use our formula, pi r squared, but since it's a semicircle, only half of a circle's area, we divide it by 2. All right, so the radius here is 1, right, because that's what this form gave me. Okay, and so the area, the exact area, is pi over 2, or about 1.57. Okay, so here comes the definition of what this has all been leading up to. So suppose a function f is continuous on an interval x equals a to x equals b, all right? Starting at a, ending at b. The definite integral of f from a to b is written like this. And what it means, it's the limit of the left-hand or right-hand sums with n subdivisions. Okay, so this means rectangles, subdivisions. With n rectangles as n goes to infinity. All right, let's go back to that picture. That is the definition of an integral. As n, as the number of rectangles approaches infinity, then, this integral is going to tell us what the area under the curve is. The exact area, not an estimate. Okay? So, so the left-hand sum, and we're not going to actually compute these integrals by hand using this limit definition, because there's a lot of rules for infinite sums that we just haven't learned yet that are going to be talked about in Calc 2. So anyway, but this is the definition, right? And basically what this is saying, the left-hand sum is, n is going to infinity. So the number of rectangles is approaching infinity, and we're just adding up the areas of all of those rectangles, using the height as the left endpoint for each of them. That's what this definition says. And now is when I come to this piece. Okay, what does that mean? So I mentioned before that this little s thing is actually meaning the sum, okay? So that's where it comes from, the sum of the rectangles. Well, what this means is very small, infinitely small widths, these x values. This is what this dx can be thought of informally is, we're taking a sum of a bunch of rectangles where dx is a tiny, tiny little width and f of x is the height. And we're doing this as the number of rectangles goes to infinity. So as dx gets very, very small is what's happening here. So that's the left-hand sum definition. We also have the right-hand sum. And so, I'm going to teach you a shortcut, just like the derivatives, but, we call these sums Riemann sums, and the function that's being integrated is called the integrand, and a and b are called the limits of integration. All right, so just some definitions to know, and really try to wrap your head around this. What does this mean? in terms of summing up infinite rectangles. Can you see that in your head? And I always go back to this little like animation thing. I mean, this is exactly what is happening here with this limit definition. All right. Okay, so here comes the fun part. Antiderivatives. So what is an antiderivative, first of all? So let's say f is the derivative of some function, capital F. Then capital F is an antiderivative of f. So let's look at some examples. So x squared is an antiderivative of 2x because 2x is the derivative of x squared. All right. X squared plus 5 is also an antiderivative of 2x. Why is that? Well, because if you take the derivative of this, we still get 2x, right? Because that constant goes to 0 when we take the derivative. So in general, an antiderivative of 2x is going to be x squared plus c, where c is a constant. C could be any number, and it would still be an antiderivative. All right. So how do we find antiderivatives? Well, there's a shortcut. So if we're taking what's called an indefinite integral, meaning that we don't have upper or lower bounds. Okay, so we're not integrating across a specific domain. So the way that we do it, it's really similar to what we did with the power rule for derivatives. We basically take each term. We take each term that's being, integrated. We add 1 to the exponent, and whatever we get is what we divide each term by. So that's this rule right here. And we're going to do a bunch of examples. I think you guys are going to pick up on this pretty quickly. Okay, so like for this one, if I'm trying to integrate this, or if I'm trying to find the antiderivative, what I'm going to do is I'm going to add 1 to this first exponent. So that's going to give me 3x squared, and I'm going to divide by whatever, I got when I did that, which is 2. All right. So the other one, x squared, if I add 1, I get x cubed, and then I'm going to divide by that. So this is it. This is an antiderivative. An antiderivative is right here. Okay. So, because there could be a constant there, we're just going to put plus c. Now, to check that this is indeed an antiderivative, we want to take the derivative of this and see if we get what we started with, right? So using the power rule, if I take the derivative of this using the power rule term by term, well, I get 3/2 x to the first, right? Or wait, I did that wrong. I have to multiply that thing on the front and then subtract the exponent by 1, right? So that's taking the derivative. Then for the second one, I do the same thing. So this is 3x squared over 3, which cancels out. The derivative of a constant is just 0. So yes, I do get 3x plus x squared from that antiderivative that I just found. So this is how you can check that your antiderivative is correct. All right. So let's go ahead and find the indefinite integral. Basically, we're just finding antiderivatives, and we're not going to forget to tack on the plus constant because that's always something I forget. All right. So again, we'll do this term by term. I'm going to rewrite this one as 2x to the 1/2 so I can, do my thing with it's not really the power rule, but maybe we can call it the anti-power rule. It's pretty, it's something I just made up. That's not a real thing. But anyway, let's do it. So, okay, here we go. So for the first one, I add 1 to the exponent, which is 3, and then I divide by that. All right, the second one, I add 1 to the exponent. Well, 2 over 2 plus 1 over 2, that's 3 over 2. Then I divide by it. That's it. I mean, I can write this, a little bit better. How about we do that? So, like, when I divide by a fraction, I'm multiplying by the reciprocal. So this is just 2 times 2 over 3, x to the 3 halves. So that's just 4 over 3, x to the 3 halves. Plus a constant. Don't forget the plus c with these indefinite integrals. Okay, so that's my answer there. All right, let's do the next one. So the next one we have, so our independent variable appears to be t. So this is understood to be the first power. So what do we have? We have 4t to the 2. We add 1, divide by what we get when we do that, which is 2. This guy I'm going to rewrite first as x to the negative 7. So when I add 1 to x to the negative 7, I get t to the negative 6 all over negative 6. Okay. Don't forget the plus c. And again, you can simplify if you want. Like this could simplify to 2. That's fine. But I'm going to leave it because I'm lazy. So that's my answer. All right. Let's go ahead and do this. Okay, so this one, I'm going to rewrite before I start adding things. So this can be written as 2x to the negative 2, and this can be written as x to the 3 over 2, right? Because the square root is just to the 1/2, raised to the 3 is 3 over 2. All right, good. So if I add 1 to 3 over 2, that's 5 over 2, right? 2 over... over 5 over 2. So that's my first one. Then if I add 1 to negative 2, I get x to the negative 1 all over negative 1. So that is my answer there. Plus c. I always forget. See? You guys are going to forget too. Don't forget the plus c. All right. Let's look at this one. So this time we have 10 cosine t. All right, well, we can't really do any of the power things that we've been doing. We just kind of have to figure out what the antiderivative is. And so the idea here is that, what are we going to take the derivative of to get cosine? Well, the answer is sine, right? So our answer here is 10 sine of t plus c. That's our answer. And you can check yourself. You can take the derivative to check. Take derivative of this to check. And you'll see that indeed you do get 10 cosine of t when you take the derivative of 10 sine of t plus a number. All right, let's see where we're at here with time. Okay. All right, here I have to do a little bit of work, which is fine. I need to go ahead and FOIL this before I start, messing around with exponents to find the antiderivative. So if I FOIL this thing, I get x squared minus 16x plus 64. All right, great. So I'm going to erase that. So we got x squared minus 16x plus 64 plus 2x dx. Okay, I can combine these like terms first. So I got x squared minus 14x plus 64. Okay. All right, so let's go ahead and find the antiderivative. So again, I'm going term by term, just adding 1 to the exponent and dividing by that thing. So keep in mind with this constant, it's really times x to the 0, So here we go. So for the first one, x squared, we add 1 to 2, and we get x to the 3 over 3. The next one, we add 1 to to 1, and we get 14x squared over 2. And then the last one, we add 1 to 0, and we get plus 64x over 1 plus c. All right, so this is my answer here. Okay, let's look at number 6. Now again, this is a special type of derivative, so we can't use that like reverse product rule or reverse power rule trick that we've been doing. So we just have to kind of think about it, like what would the antiderivative of e to the x be? Well, it's just e to the x, right? So what's our answer here? Well, it's just going to be e to the x minus 20x plus c. And to check, again, take the derivative of this. Do I get this? And yeah, you do. You should get that. So that's the answer there. All right. So directions. Find two antiderivatives for each function. So remember that an antiderivative, we do that reverse power rule business, and then we add on a constant. So here, one antiderivative, we can just say, well, it's just x to the 3 over 3 minus 4x squared over 2 plus 7x over 1, and then plus 0, right? That's a constant, so I don't even have to write that. So here's my first antiderivative. Super lazy. The second one, well, I can just change my constant. Instead of doing plus 0, I can say plus, I don't know, what do you think? 108. Just a random number that I just made up. And by the way, there's infinitely many antiderivatives here, right? All we have to do is just stick another constant in there, and that would be an antiderivative. So there's 2 of them. Let's look at the other one. Let's look at number 2. So first thing, we need to find the derivative. So what do I have to take the derivative to get sine? Well, the derivative to get sine is not just cosine, right? So if I take the derivative of cosine, I get negative sine. So here I need to tack on a negative, right? The derivative of negative cosine is positive sine. Now, what do I need to take the derivative to get cosine? Well, I need to take the derivative of sine to get cosine. All right, so here's 1, plus 0, okay? Plus 0. That's one antiderivative. If I take the derivative of this, am I going to get this? Yes, you are. Okay, let's do another one. So my second one, I can keep everything the same. Instead of plus 0, I can say plus whatever I want. Plus 82. Who cares? So that's my second one. I could do negative cosine x plus sine x plus pi. I could do plus e. Any kind of constant number will work. And e and pi are numbers, by the way. Okay, let's see. Oh, I have another one hidden down here. All right, well, just like with the power rule, I'm going to simplify this first so I can add exponents and all of that. So when I simplify this before doing anything, this is going to give me t to the 5th, right? Keep the base, add the exponents when I multiply, plus t to the 3rd, okay? So now my first antiderivative, well, I have to add 1 to 5, so that gives me t to the 6 over that, which is 6, plus add 1 to 3, t to the 4 over 4. So my first one, I always do plus 0 because I'm lazy. So let's do the second one. The second one is the same thing, except maybe I can put on another number. Like, instead of plus 0, how about plus pi over 5? I don't know. So that's my second one. All right, let's see. We're right on time. All right, I'm going to go ahead and stop this video. I'll see you guys in the next one. Thanks for watching. Okay, guys. These are some properties of integrals, and we've sort of done these, in problems before, but these are the official properties. So if k is a constant, we have the indefinite integral of k dx is just kx plus c. E to the x, of course, is just e to the x plus c. And the indefinite integral cosine of x dx is sine x plus c. Sine x is negative cosine x plus c, and yeah, we've done these, but this is just kind of official, so you can have these in your notes when you're doing your homework. All right, we also have this one, okay, so the indefinite integral of 1 over x dx is equal to ln absolute value of x plus c. So why is that the case? What's up with the absolute value? Well, because if we took the derivative of just ln of x, positive x, well, that's going to be 1 over x, right? But also, if we took the derivative of ln of negative x, we would have to use the chain rule here, right? And that would just be 1 over negative x times the derivative of the inside, which is negative 1, giving us, again, 1 over x. So the absolute value is coming from the fact that this could be a positive x or a negative x. All right, so yeah, so the indefinite integral of 1 over x is ln of x, absolute value of x plus c. So let's go ahead and do an example here. So this, if the indefinite integral of 1 over x is ln of absolute value of x, well, this is just going to be 6 ln absolute value of x. This guy, before I give the antiderivative, I'm going to rewrite it as 20 x to the negative 2. So if I add 1 to the exponent and divide by that number, I get 20x to the negative 1 over negative 1. But remember that negative is here, so we have this. And so basically, if you want to write this a little bit better, this is going to be plus 20x to the negative 1 plus c, because it's indefinite. There we go. All right, some other properties. So if we have the sum, or if we're taking the integral of a sum or difference of functions, we can split it up in this way. So we can split up the sum or the difference respectively. Another property is that if we have a constant being multiplied by some function that we're trying to integrate, we can just pull the constant outside of the integral. Okay, so we talked about indefinite integrals. We talked about definite integrals in the very beginning of the lecture. Basically, so we looked at triangles on a specific interval from x equals 0 to x equals 1, and we were trying to find the area under that curve. So that was definite because, the upper and lower bounds were defined, whereas with indefinite integrals, we don't have upper and lower bounds. It's just, over the domain is pretty much, it's an undefined domain, right? So here, we do have an upper and lower bound, and what I'm going to briefly touch on is something called the fundamental theorem of calculus. We're going to go into this more in next week's lecture, but for the purpose of this lecture, I just kind of want to briefly talk about what it is with the purpose of doing these, integral computations. So the fundamental theorem of calculus says that this is the way that we can evaluate definite integrals. Is basically we find the antiderivative, and then we plug in our upper and lower bounds into that and subtract them. Okay, so that's how we do this. And fundamental theorem, so it's pretty important, right? So let's go ahead and do a bunch of examples with this. Okay, so we do have definite integrals, and there's no plus c because there's no what's the constant? It could be any constant. No, this is a definite integral. So we're given a specified domain that we're integrating on, and we'll use the fundamental theorem of calculus to do that. All right, so the fundamental theorem says we're first going to take the antiderivative here. All right, so we take the exponent and add 1 to it and divide by whatever we get when we do that. All right. So then I'm going to put my bounds here, lower bound to upper bound. And the fundamental theorem says that what I'm going to do is I'm just going to plug in the upper bound first in for x. And then I'm going to subtract plugging in the lower bound for x. So this is like f of b, capital F of b, the antiderivative plugging in b, minus capital F of a. That's what that is. So let's go ahead and compute this. 3 times 2 to the third over 3. Let's see what we get for this. This is going to give us 8 minus 1, which is going to give us 7. All right, so the area under this parabola from x equals 1 to x equals 2 is 7. That's the exact area, which is super cool. All right, because again, we're dealing with a parabola here. This is a weird shape. This is 1, 2, and then, I don't know, maybe it looks like this. So this area right here is 7. All right, let's do another example. So first things first, I'm going to rewrite this as t to the negative 2, so I can do my little antiderivative trick. Okay, so I'm going to take the antiderivative. So if I add 1 to this, it's t to the negative 1. Add, divide by whatever that is, negative 1. And then I'm evaluating from 1 to 3. So I'm going to first plug in 3 into this. So this is going to give me, n for t, 3 to the negative 1 over negative 1, minus, now I'm plugging in my lower bound, 1 to the negative 1 over negative 1. All right. Okay. And so when I simplify this out, I'm going to end up getting 2/3. So that is the area under this curve from x equals 1 to x equals 3. 2/3. All right, let's do some more examples here. So again, I'm going to first find the antiderivative. So term by term, the first one is 2x to the 4 over 4. The second one is 4x squared over 2. And the last one is just minus x. And I'm evaluating from 7 to 9. So I'm going to go ahead and plug in 9 first. 9 to the 4 over 4 plus 4, 9 squared over 2 minus 9. And I'm subtracting from that, plugging in my lower bound. 2 times 7 to the 4 over 4 plus 4 times 7 squared over 2 minus 7. And let's be careful to make sure that this negative stays on the outside. Once when we distribute that negative is what I'm trying to say. Make sure you do that. So what you should end up getting, if you do this in the calculator, is 2,142. That's the area under this curve from x equals 7 to x equals 9. Okay. All right, let's go ahead and let's look at this next one. We have 2e to the x. Well, this one's easy. So what's the antiderivative here? It's just 2e to the x. When I take the derivative of this, I get exactly this. And I'm evaluating from lower bound is 0, upper bound is 1. So plugging in 1 first, I have 2e to the first minus, now I'm going to plug in 0. And if I simplify this, I just get 2e minus 2 is my area under this curve from x equals 0 to x equals 1. All right, let's go ahead and do this example. So first thing, I'm going to find my antiderivative. So the first one is x to the 4 over 4. The next one is pi x to the 3 over 3. And my bounds are from 2 to 5. Okay, so the first thing I'm going to plug in 5 into my function, or into my antiderivative. So I get 5 to the 4 over 4 minus pi over 3 times 5 to the 3. All right, so that's my first bound done, minus my lower bound. Okay, so my lower bound is going to be 2 to the 4 over 4 minus pi over 3 times 2 to the 3. And when I compute this, let's see what I get. I get this weird number, 609 over 4 minus 117 pi over 3. So this is the area under this curve from x equals 2 to x equals 5. All right, finding exact areas. So remember in the very beginning of the lecture, I talked about areas versus integrals. So when we're taking integrals, we want to make sure that, we're giving the appropriate signs, based on whether or not we're above or below the x-axis. And so what I want to do here is, because I'm looking for areas, I want to, and not the actual integral value, is I want to basically separate these areas based on above the x-axis and below the x-axis. So, I know what the signs are, and it doesn't get lost in translation with the integral calculation, okay? So, all right, so if we look at this graph, I just put it in Desmos. We're looking for the area bounded by the x-axis and the graph. So we're looking for this area right here and this area, and we're just going to sum them up, right? And how am I going to do it? Well, I'm going to separate the integral so that I can find the area, and make sure to give the appropriate signs to each area. So with the first one, actually, I'll do this in black. We're starting at x equals -1, and we're ending at x equals 0 for this black portion. And I'm doing x to the third minus x dx. Okay. All right. And then for the second piece, I'm going from x equals 0 to x equals 1. So my lower bound 0, my upper bound is 1. Same function. But what I want to make sure of when I do this is that, I make sure that there's a negative on the outside, because my answer is going to be negative, but since I'm looking for the sum of the areas, I want to make sure that my, both my areas are positive, basically. When I do the integral, when I take the integral, it's going to take into account whether or not it dips below or above the axis. So we're trying to kind of get away from that here. All right, so the first one, I'm going to do this down here. Well, first thing, I need to take the antiderivative, so that's x to the 4 over 4 minus x squared over 2, and I'm evaluating from -1 to 0. All right, so what I have is plugging in 0 first, I get this, minus, now I plug in -1. Okay. Computing this, I get a fourth. All right, so that is this black area. Let's put that off to the side. Now let's do this, remembering that we have to make our answer negative. Okay, so again, we have the same antiderivative as before, but this time our bounds, and we're making it negative, our bounds are from 0 to 1. So computing this, well, we end up getting, 1/4 minus a half at the end of the day, and so we end up getting negative 1/4, but of course we're going to make this positive, so also the area here is 1/4. Therefore, the total area of these is just 1/4 plus 1/4, which is a half. And that is my answer for this one. All right, guys, I hope these videos were helpful. Thanks for watching, and see you next time.